Well, thanks for joining us for this symposium. I don't know whether I should say good morning, good afternoon, good evening, or good night. It really depends on your time zone at the moment. We have 4 speakers for you today talking about learning to count, new insights on the acquisition of symbolic numerical knowledge. The first speaker is going to be Emily Slusser. Then we have Attila Krajcsi, then myself, and then Darko Odic. We really hope we are going to give you a nice overview on new insights on learning to count, on how it is, I would say, difficult to understand what young children understand about symbolic numbers. So without further ado, Emily, the stage is yours.
Fantastic. Let me go ahead and click over to my screen. I'm hoping everybody is seeing the presentation view of my slides. Fantastic. Yes, not all of those notes that I have to myself, which could be incredibly embarrassing. Thank you so much for having me here today, and welcome. Like as was said, people coming from everywhere today. I certainly wish we were in Dublin many weeks ago, but this format is working very well, and thank you, Andy, for doing this. And to anybody here on the West Coast, props for getting up early. I'm thrilled to be here today. Okay, so I'll start this symposium off with a talk that is showcasing some of the emerging findings that we have from an ongoing study, one that we had hoped to have wrapped up, but due to current circumstances, we're still kind of paused with data collection. Nevertheless, we have some emerging findings that I think will be of interest and certainly in alignment with the other talks that have been scheduled for this particular hour. So the title of the talk today is Size versus Number. So what we're looking at here is how children are assigning number words to various dimensions of quantity, knowing that they're recognizing both continuous and discrete dimensions of quantity as they work their way through this long and somewhat arduous process of learning individual number words and constructing a natural number list. I'm going to be presenting on behalf of myself and my colleague, Dr. Carvalho here at San Jose.
Let's switch on the light.
All right, so my overview for the talk is super straightforward. Like I said, it's one study. We'll be going through results on multiple tasks and then ending within the 10-minute, 12-minute time frame with some conclusions and some ideas for future directions. So I'll go through the background information relatively quickly. Again, if we had all been in person and in Dublin, I think I would be pointing to other talks that we'd have experienced over the course of the day and recognizing that we're building on relatively similar premises, or at least I'm assuming that would be the case. So the premises that I am building this off of is that children have this capacity for representing number early on in the course of development. With 2 different systems, both limited, but both very powerful in their own way. So we have a system for representing small exact numerosities, and we've seen that time and time again through many different methods, but here I'm just representing the box crawl task where you put 2 cookies in one box, 3 cookies on the other, put the infant on the ground, which one do they crawl towards? The one that has 3 is going to be more enticing for somebody who's seeking out cookies. What this is representing to us, what this is revealing to us is that these young infants, and even before they're able to crawl, can discern the difference between 2 and 3. And they can do so even when controlling for continuous quantity. So you'll see that the cookies in the right-hand box are a little bit smaller than that on the left, and yet they still are able to discern the numerosity is bigger. And the other system that we're building off of here, and I'm not acknowledging for this line of work, is that large approximate number system, ANS, or analog magnitude system, goes by different names. Recognizing here that, again, from infancy, children are able to discern the difference between approximate quantities. And again, we're looking at both numerosity and elements of continuous quantity. So total summed spatial extent, total summed area, total summed contour length. We're sensitive to many different dimensions of quantity, and I'm emphasizing that point because it's going to come up a little bit later on. Now, the other kind of underlying premise for this talk is that the construction of exact number concepts is actually a very long developmental trajectory that we know takes place from birth over to the course of 5 or 6 years into development. So you'll see on my timeline here with the large, approximate, and small exact number representations happening at or shortly after children are born, but then the ability to recite the count list emerging several years later, 1 or 2 years later, and then the series of knower levels that will be progressing through over the next 2 years or so up until we induce or at least learn the cardinality principle and successor principle. So my work is oftentimes focused in what is bracketed at the top, those 2 years, sometimes 3, where children are working their way through the construction of individual number concepts, large exact representations that exceed what is possible from those 2 inherent systems that I discussed on the previous slide. Like I said, I've done a lot of work with knower levels as they've been defined in previous literature, and taking many of those data together. This is a meta-analysis of 300 students, children, and it's their knower level. How many number words do they know the precise meaning of up until they have induced a cardinality principle and can therefore count to determine the number of items in the set. Plotted against age. So what I tend to point out here is that, yes, there is a progression in age, as it obviously going through these knower levels does take time, and that's reflected when you look at a cross-sectional sample of lots of children. But at the same time, if you take the mean age for this particular sample around 40 months, that 40-month child can fall in any one of these knower levels. We can't necessarily predict based on age which knower level they will be in necessarily. So what I'll do in this talk is align their performance on the various tasks that we'll be discussing to knower level. Not so much age, we'll probably control for age, but really how many number words do they know? Where are they in this knower level trajectory? And as they move through that trajectory, what do they know and what are they learning about number? So we tend to focus on the large exact definition of number, but in fact, they're learning many other things about number during this period of time. And the thing I'm going to focus on here is that numbers in general refer to discrete count quantities. I'm going to build off of Sonia and Gelman's work for this particular line of research. Just back in 2004, it's a hefty report, should you go and look it up, or if the authors are here on the line. One of the tasks that they report on is called a transforms test, sets task. That's what they labeled it. In that task, what they did was they had a box, an opaque box, one with a lid, and then they dropped items in that box, closed the lid, did a quick number check. I put 6 balls in the box, for example. How many balls are in the box? And then we would check to make sure that they at least remembered the number of items in the box as we had labeled it. And then the transform piece comes through the fact that they would close the lid and then they would either shake the box, turn the box around, or they would take an item out or add an item in. So of course, the shaking and rotating elements of that task don't change the numerosity. They don't change the number of items in that box. But if you add one or take one away, it does. So what they were looking at, and I won't spend too much time aligning your attention to this figure. Maybe you can just trust me for it, but you can always go up and look for that original citation. What we found, or what they found, was that young children did not change the number word when the box was just non-numerically transformed, shaken or rotated, but they did know to change the number word when an item was taken out of the box or placed into the box, added to the box, showing us that young children do understand, even if they don't understand exactly what the word 6 means, they do understand that that number word is used to label the numerosity, the number of items in that set. So I'll say the takeaway here is that these young children and the levels as they're represented in this figure here align with the knower levels that I introduced just earlier. The number word does not change when it's shaken or rotated, but they do understand that it does change when an item is added or removed from the set. And we're seeing that pattern existing across knower levels. So from very early on, children are assigning number words to number. Fast forward a couple years, I'm working with my graduate advisor, Barbara Sarnecka, and in 2011, we published a study that looked at a very similar question. Here, again, looking at what children understand number words to mean in general, not precisely, but in general, as a class of words that they have in their vocabulary, what are the semantic constraints? So in this study, we had a match to sample design. And so we presented a picture of 4 turtles, for example. This was our sample picture. And then we presented them with 2 options. Can you match this picture with either the one on the left-hand side, which has the same number of turtles, or the picture on the right-hand side that has twice as many turtles, but is matched in this case on summed contour length. So the question was, if you prompt them with a number word, this picture has 4 turtles, find another picture with 4 turtles, can they match on number? Again, not necessarily needing to know what the precise definition of 4 in this example is, but are they attending to that element of, or that quality of number when they're matching these pictures? Something else to point out is that we had trials that matched on mood. That's why you see happy and sad turtles, and then on color. So we have orange and green turtles. So in various different trial types, we had controls or distractors on these different dimensions. What we found from that line of work was that children were able to match based on prompts for mood or color. So find another picture with green turtles, they did pretty well. Well above chance, and you'll see that in the light blue bar for our subset knowers, and that's going to include our 1, 2, 3, and 4 knowers, those who have just an understanding of a subset of the numbers in their count list, and that is compared to the CP knowers. Those are our cardinal principal knowers on the right-hand side. So matching on mood and color, fine. But when it comes to numbers, so that's the previous example, can you find another picture with 4 turtles? The subset knowers are performing actually below chance, indicating that they're inclined to match on some other dimension, maybe mood or color. Whereas the CP knowers know when prompted with a number word, they'll go ahead and match based on number. Okay, so based on this, and of course a whole a broader range of work that looks at what children know as they work through these knower levels and what they need to learn, we developed a new study that pulls in that element of continuous quantity, in this case size, total area, we looked at it not controlling for that, as we have done in so many other lines of work, but in fact, exploiting that, really trying to figure out if children are distracted by various elements of continuous quality when they're assigning number words to numerosity. So when and how do children come to understand that number words refer to discrete countable numerosities? They are not used to characterize, as our approximate quantifiers are, broadly a general amount, a lot or more. Do children think that number words change as the individual items in the set or size in the set grow or shrink? And then we also looked at executive functioning, knowing that we have building understanding of how executive functioning plays a role in this developmental trajectory as well. So what we're doing is looking at 2 to 4-year-old children. So far we've tested around 50, half male, and the average age is just over 3 years old. We did 3 tasks. The first one is a give a number task, extended from Wynn 1990, 1992. We have a collection of 15 fish. We ask the children to put various set sizes in a bowl so as to evaluate their understanding of those individual number words 1 through 6. Based on their performance, we assign them to a knower level. If they know 1 but not 2, they're a 1 knower. If they know 1 and 2 but not 3 and 4, they're a 2 knower, so on and so forth, up until they understand, like I said before, the cardinality principle. We also administered this executive functioning task. So we're going to deem that elephant crocodile based on some work that Andy alluded to earlier when we were back at the Wesleyan Cognitive Development Labs. Very much like the day-night tasks and some of the card dimensional card sort tasks, this one has 2 puppets. They're asked to, when following the rules of the elephant, ask to press the same button that the elephant presses. And then the crocodile, the tricky crocodile, when the crocodile presses a button, you press the opposite button, the other button, the button they didn't press. So in doing so, and multiple trials of this, and then starting to mix up rules between the elephant and the crocodile, administering trials simultaneously, or at least sequentially right after one another, we're measuring their executive functioning skills as defined by their impulse control and their cognitive flexibility. So Francesco, I'm speaking quickly, and I just want you to call out when time is up.
Yeah, time is up actually.
So, okay, well, that's all the background leading up to my talk. I will go ahead and introduce really quickly. Can I get a minute?
Yeah, sure. Darko is not here yet, so yeah, just
okay.
go.
Okay, and I can just pick up if Darko doesn't come in, I'll fill up that space. We developed a task analogous to that initial transform sets task. But in this one, while we have number trials where an item goes in and out of the box as per the one where we had the original physical elements, this one, because it's programmed on a computer, will also allow the set to transform based on continuous quantity and not numerosity. So in this case, we will add and subtract a leaf from the box, but in some trials we'll have pumpkins and then we'll watch them grow or we'll watch them shrink. And then we have non-number, non-quantity trials where the elements will simply line up or spin around. And I'll leave it at this since we're out of time, but I'll just show you the emerging trend here is that we see children succeeding on these number trials at an intermediate stage of number word development. So around the 3-4 knower level, they're performing above chance. And that's likely, I'll get into the details should we have time to revisit it, but we're starting to look at what number words they know and how that is contributing to their performance here. So as you transition to the next speaker, why don't I just go ahead and leave you with a conclusion slide. And should we take questions at the end then?
Yeah, it's better now. Unless there is a very quick question. If there is one that is very quick, please speak now. Let's give some seconds to people. No. Okay, we can go ahead. So thank you. Right. Thank you very much.
Thank you.
Good. Now, second speaker. So, Attila, is your turn. Can you share your screen with us?
I just have to share my screen. That's it, I guess. Can you see that?
We can see, but it's not in the presentation mode.
Oh, really? I can see it. Well, let's just try to start it again.
Yeah, no, it works. Yes, okay. Yes, it works.
Great, just a second. And still you can see the presentation, right?
Yeah, now it's in the presentation mode. We can see it.
Okay, and can you see my
yes, the pointer as well. Yes.
Pointers, okay. So thanks. Also, thank you for the organizers for having this nice symposium. And I mean, the whole conference and specifically Francesco for this symposium. And this talk today, I'd like to talk about a few issues with the given number task, and trying to show some data that demonstrates that maybe we should refine a few properties or features of this task. This whole slideshow is a bit more detailed than having that in 10 minutes or 12 minutes. So at the end of my talk, I will send the link of this Google Slides to the chat, so you can check some more details of that. But in my talk, I will skip some of the slides. I will skip the outline slide, and also because I suppose that everyone knows, what the given number task is, and even if you don't know, Emily gave a very nice introduction. So, we are measuring how preschoolers or small kids understand symbolic numbers or number words, and based on that information on the task, we are categorizing them into pre-numeric, subset numbers, or CP-number guys. And usually we are supposing that CP numbers are somehow conceptually different from subset numbers, and that was the original starting point. But in the recent years, there are more and more data showing that maybe this is not the case, because even if CP numbers are supposed to know a lot of things, not all of them know, for example, estimate this 4 items, or more than 4 items, I mean several items, or compare symbolic numbers, or understand when a item is added or removed to or from a set. And again, we are supposing that they should know that, but still they don't know that. And my point today is that maybe those conceptual issues partly come from some methodological issues with the task, with which we are kind of diagnosing the kids, whether they are subset knowers or CP knowers. And let me list you four problems. I will very briefly mention the third one, but I will explain a bit more details the others. So the first one is that usually we are supposing that there is a breakthrough after understanding 4. So for example, if a kid understands 5, then we are supposing that she or he can give you 6, 7, and so on, all the objects, all the numbers in their counting list. Now, one problem is that if you're looking at the literature, sometimes it's reported that there are 5 knowers, 6 knowers, 7 knowers, so kids who can give you numbers up to 6, but not beyond. And based on our standard model, this is impossible. So we just made a simple measurement whether this kind of large number subset knower pattern is frequent or not. And so we have 2 data sets at the moment with 72 kids per data set. All of them are 3 and 4 years old preschoolers. And we asked for numbers between 1 and 6 and between 1 and 9, depending on the 2 data sets. And our question was whether we can find 5, 6, 7, and so on knowers. And we also calculated numbers with different methods, but because I don't have too much time, let me just skip this one. I will talk about the first calculation method. This is just like it's imitating the titration, the classic calculation method. So here you can see the results for the first data set and for the second data set. And also you can see a distribution of the kids based on their number knowledge, based on the classic calculation method and the new calculation method. And as I told you, I will just ignore that. So you can ignore the y-axis and that dimension. The point is that in the first data set, we could see 5 knowers. And in the second data set, we could see 6, 7, and 8 knowers. Okay, so clearly there's no breakthrough in their knowledge if we can trust those data. But these are just the standard methods. And one might ask that, okay, why Karen Wynn couldn't see that? And my best guess is that probably she had small samples. So in her classic papers had 20 and 19 persons in her sample. And as you can see, 5, 7, 6, 7, and so on knowers are pretty rare. they are much more rare than classic subset knowers. So maybe she couldn't observe this because of the small sample size. And we had very important methodological consequence for this. So if this is true, then it means that there are a lot of 5 knowers, 6 knowers, and so on, who will be categorized as CP knowers, even if they are not. Okay, so that might explain some kind of noise in our data. Now, the second problem, that usually we are supposing that this number knowledge is all or nothing. So either a kid knows a number perfectly in a given number task, or doesn't know anything. Now, what you can see here is the very same data I have just shown to you, but here every single row is a single kid, and the columns are the mean performance for giving 1, 2, 3, and so on. And green means a perfect performance, and 0 means that they couldn't give it correctly at all. And the kids are ordered by their mean performance. And first of all, you can see some usual things here, what you would expect. So for example, this little guy is a 1 knower. He or she knows number 1, but doesn't know any other numbers. Here you can see some CP knowers, or at least 6 knowers, and they know everything. But what is more interesting is that part of this chart. So for example, here you can see 2 or 3 knowers where they are pretty sure about small numbers, and they don't know anything about, for example, 6, but their performance is somewhere in between in this middle range. So, it's not all or nothing, but their knowledge is gradual. And this could be important if you're using, for example, the classic titration method, because let's suppose that we are measuring numbers between 1 through 6, and you're measuring the performance of the kids. And let's suppose that we have this gradual real ability of giving numbers. And because you are using only 3 trials per number, obviously this measurement will be much more noisy. And we have some threshold for our criteria. And whenever the kid's performance drops below this threshold, that will be their measured number knowledge. And here you can see that this extra noise could really cause some bias in the measured number knowledge. Okay, so the point is that with this gradual knowledge and adding some extra noise and using the titration method, you will introduce some noise into your data. Now, the third problem, I will just mention this very briefly, is that there are a lot of versions of this task, and usually we are supposing that all versions work the same way. Okay, so no matter which version you are using, they could be just technical things, but finally you will measure the very same number knowledge. Now, in the example of follow-up question, there are a lot of versions, and sometimes, follow-up question is at the end of the trial, we are asking, could you recount that set? Can you make sure that your set is 3 as I asked you, and so on. And there are a lot of versions of that. And originally, Karen Wynn supposed that this is required to overcome performance error, but also this would introduce a training effect. So no matter whether you're using those follow-up questions or not, maybe there could be some differences because of these performance error or because of these training effects. So we checked a few versions of those follow-up questions. And let me just very briefly concentrate on this chart. These 3 columns are the 3 conditions or versions of the task, and y-axis is the number knowledge, the measured number knowledge. So, whether they are 2 knowers, 3 knowers, and so on. And the main result is that in the recount version, the measured number knowledge is a bit higher than in the other 2 conditions. The point is that depending on the version of the task, you will see different number knowledge. Okay, obviously, this will introduce a difference between papers using different versions, so you will not be able to compare those studies. Now, maybe the most surprising part comes as the final problem. Originally, Karen Wynn argued that there are two reasons why we can suppose subset knowers and cardinality CP knowers. One main reason was that we can see this sudden drop beyond 4 in their performance, or there's a breakthrough. Now, as I mentioned to you, probably this breakthrough is not there. But the other argument why we can see qualitatively different two groups is that subset knowers and CP knowers collect the items differently. So subset knowers are usually grabbers and CP knowers are counters. Now, the problem with this argument, which was recognized by Karen Wynn, is that when you're working with large numbers, you will not be able to grab them. So you cannot grab like 6 objects. You cannot subitize it. Your hand is not large enough, or your movement is not fine enough to grab all the 6 objects precisely. So probably when you're working with large numbers, you have to count. And so CP knowers who are working with larger numbers usually will count because they cannot do otherwise. And this was recognized by Wynn, and she said that for this reason, you have to concentrate on small numbers, how those kids are handling these numbers, the small sets. And she argued, and here you can see that for small numbers, the CP knowers count more than the subset knowers. And that was the argument, why there's a qualitative difference here. But here's a problem. So let's suppose that you're a CP knower and you have already learned that large numbers can only count but not grab. Maybe you can overgeneralize this kind of strategy, not because it means some kind of conceptual change, but because that's, first of all, that's the only way you can enumerate large sets. And also kids tend to be a bit rigid or strict using the rules. So maybe they are saying that, okay, I could grab 3, but I will count because I want to be a good kid or something like that. So maybe the fact that CP knowers are counting small sets is not a sign of a qualitatively different representation, but maybe it's just a strategy choice or an execution problem. And also, we have measured, and that will be almost my last slide, and sort of probably my time is up, right? Yes, it's the last slide before the last one. So we have measured some strategies in different number knowledge kids, and what you can see here, when they were asked for 3, which strategy they used. And here you can see 2 knower, 3 knowers, and so on. And 5 knowers are classically categorized as CP knowers. And the point is that they are, and this is an extreme example, even in our data set, but they are grabbing as much as smaller kids. So, and sometimes, we can see that, okay, they are grabbing less. But my point is that even in that case, that may be not enough for a very specific validation. So here's my last slide and my conclusion, that there might be a few problems with the given number test. Maybe we are categorizing large number subset knowers incorrectly as CP knowers. Maybe we are introducing unnecessary noise with the current method. Maybe some of the test versions are not comparable across studies. And maybe the whole validity of the given number test could be questioned. So my suggestion is that probably it would make sense to reconsider and/or reanalyze former results based on those issues and some related issues, or even replicate former findings if it's necessary to see those results more clearly, what is already available in the literature. And also, if we have those data, then we can see whether the given number test could be fixed or not. And if it cannot, then maybe we could look for some other tools that could kind of validly diagnose or reveal some qualitative different change in preschoolers' mind more validly and more reliably. And I guess Francesco will talk about some alternative ideas like that, and that will lead us to the next talk. And thanks very much for your attention. Here you can see the website of our lab, where you can see some more materials related to this project. Thank you.
Thanks, Attila. Let's see whether there is a quick question. Quick question. Anyone? I'm just waiting a few seconds.
Can I?
Yes, sure, Christoph.
Hi. So, like, this is really interesting, and I really like the approach. And I just wanted to ask whether just simply adding more trials for each number would somehow solve, or it produces more error or more problems than it solves.
Yeah, partly we were experimenting with that. So usually in the standard method, you are measuring 3 trials for every single number. Well, we introduced a 4th one, and we compared, the patterns and stuff like that. What we could see is that everything is smoother, but it will not change qualitatively. So having more trials partly makes the data less noisy, but in itself, it will not solve most of the issues.
Thanks.
Okay, thank you. Now it's my turn, though. Okay, let's see whether this works. You should see my screen now, or at least I hope so.
Yeah,
let's see whether it works. Okay, great, perfect. Thank you for joining us again. One of the advantages of organizing a symposium is that there is no need for me to explain a lot about the theory and etc. So I can jump immediately into the talk. Well, we have been talking a lot about the given number task. And what I want to make clear is that in this there is this developmental trajectory here. I mean, like in the given number task, and children at the end they become cardinal principal knowers. And what they are supposed to understand is this successor function, basically understanding that adding one object to a set corresponds to the next number word in the counting list. Sarnica and Carey use this unit task to measure this ability in cardinal principal knowers. I mean, a very simple task called the unit task. Children will show the box with some strawberries, for instance, inside, and then one item was added. Let's assume for a moment there were, like, I don't know, 4 strawberries inside. One was added. Of course, children were asked whether now the box contains 5 or 6 items. You would expect at this point that cardinal principal knowers should be able to perform the task correctly. Indeed, they are, but as you can see, their performance is above the chance, but they're not a ceiling. Another task that was used is this direction task, in which 2 plates are presented, and then one object, I mean, 2 plates with the same numerosities, 5 and 5, and then one object is moved from one plate to the other, and then children are asked which one now has 6, which one now has 4. And as you can see, again, we have cardinal principal knowers are able to perform the task, but they are just above the chance level. They are not at ceiling. There is another principle that cardinal principal knowers can show, and this is this later greater principle. How is it measured? With a numerosity estimation task, in which children are just show a set, and they have, without counting, to estimate the numerosity of the set. When, of course, there are like few objects, up to 4, you have all children are able to perform this task quite accurately. So you can see that the estimates, I mean, there is like a linear relation between the target numerosities and the estimate. It gets more interesting outside the subitizing limits in the domain of the approximate number system. As you can see, CP knowers can be divided into groups, mappers and non-mappers. You have non-mappers that every time a large numerosity is showed, they tend to tell you the same number, like 7, 7, 7, or 10, 10, 10, without showing this linear relation. Instead, mappers are able to do that. It seems that mappers have understood the later greater principle. They know that when they see more dots, they have to tell you a number word that is later on in the counting list. What is interesting is that mappers are also able to compare large number words, small and large number words. So it seems that this later greater principle helps them to understand the magnitude of number words. We found something like, I would say, a parallel study done with the number line task. Again, we ask CP knowers to perform the number line task that I'm pretty sure everyone is familiar with. I mean, number line with the interval from 1 to 10, and children have to place some numbers on the line. And as you can see, again, we have found this distinction between spatial mappers and non-spatial mappers. The mappers are those that are able to place numbers in a linear way on the number line, and non-mappers, they're not able basically to perform the task. They tend to place all the numbers in the middle. What is interesting, again, is that we found out that children that are able to place numbers on the number line are also able to tell you, I mean, which digit is larger. We have explored this more, and we have found out that actually is order that matters. If children are able to place digits like this one, you present them with 8, and then you ask them, where would you place 7? And the child places 7 here, and then where would you place 9? Of course, it goes here because it's 7, 8, 9. If you're able to perform this spatial order task, they're also able to tell you, or at least it relates, there is a correlation with the ability to compare numbers. So far, I mean, like, we have all these principles and rules on what side that children must know about the counting system. And on the other side, we have the symbolic magnitude. This is so important for them to understand magnitude, I mean, symbolic magnitude, because it's one of the most important predictors of later mathematical achievement. So, I mean, several studies have tried to establish a relation between these two things, principles and rules on one side and magnitude understanding on the other side. I'm going to present you one study today that we did with preschool children. We started by asking them to perform the given number task with all the caveats that Attila before mentioned, and we classify children in CP knowers and subset knowers. But as you can see in our sample, we basically had 80 CP knowers and 9 for knowers, so we could assume that children were actually able to understand the cardinality principle. We also asked them to perform a forward numeration task, very simple. They had to reset the counting list. We allowed for self-correction, well, we stopped them when they reach 100. As you can see, there was a lot of variability there, but we were sure that all children were at least able to reset the counting list above 16. Then we asked them also to perform a naming task to read some numbers, basically, and also we asked them to perform the Krajcsi block and forward digit span. These were kind of domain general control measure. Before going ahead, if you want to see something like some results that are similar to this one, probably it'll be more complicated, I would say please take a look at this paper that we published recently. So as I was saying, we also asked them to perform other tasks. The first one was this simple dot comparison task, in which we ask children to simply say what was the larger set here. The ratio, I have to say, was just 1/2. This was a very simple task. Indeed, basically all children were at ceiling. This was just to be sure that children understood the meaning of more, of numerically more, and they were able to perform this task. Then we asked them to perform a numerosity estimation task, very similar to what Loughborough did. There were 4 target numbers, each presented twice. They had just 1 second. Of course, they couldn't count, but they had to provide an estimate. Now, we created a kind of novel direction task. Well, I mean, novel was kind of inspired based on the study by Sarnecka and colleagues. The idea was very simple. We presented children with the child with the box, and the box were some balls, and we said, oh yeah, in this box there are n balls, and then we asked them to confirm the number, just sort of a memory check. Then in some trials, 1 ball was removed, so n-1, and in some trials 1 ball was added. And then we asked them, how many now? There were 4 target numbers, 2, 8, 13, and 17. We did something very similar, but this time based on spatial order in the number line. We present children with a sensor number. These were the C-1 trials in which we presented children with the sensor number. Let's assume this was 2, and here there was 3, and the experimenter went in this box here, there is the number 2, here there is number 3, what number goes here? And in the C+1 was like in this box, there is the number 2. Here you can see the number 1. What number goes here? And again, same starting numbers, 2, 8, 13, and 17. Then number comparison. We asked them to perform a number words comparison, in which we present all these comparisons. As you can see, these are the same numbers that were used in the other tasks. Was done completely verbally or completely kind of visual with the 2 numbers presented visually. So results. Numerosity estimation tasks, this is exactly what one would expect. Almost all children correctly estimate 2. Okay, this was kind of easy. Then you can see that for the other numerosities, there was a tendency to provide larger estimates, and that was good. We were, as you can see, one target was 8, and the other one was 17. We were sure that children could perceive the difference between the 2 sets, because we asked them to present the simple dot comparison task, in which the one set was double the other. So in this case, 8 versus 17 is more than double. So we were sure they were able to perceive the difference. But as you can see, something that happened very frequently, a lot of times children said 10. Always 10, always 10. This is large, so it's 10, 10, 10. These are the children that usually are classified as non-mappers. Indeed, we have, based on the same criteria that Lor.nd and Krajcsi used, we had some children that showed this linear relation between estimates and the target numerosities, so they were mappers, and 49 of them were non-mappers. And then we reclassified them based on the fact that they were also CP knowers or not. Direction task, this kind of a reminder, n-1, n+1. As you can see, this is the proportion of children. All children were able to perform n+1 and n-1 when there were just 2 balls inside the box. As soon as you go out of the, let's call it object tracking system limit, you can see that children are able to perform n+1, but most of them, but fewer are able to perform the n-1 transformation. What is even more interesting are the errors that they do. This is just recensored based on the trials. N is the starting number of balls in the box, and then this is kind of very interesting, because in the n-1 trial, when they gave the wrong answer, they said +1 a lot of time. So as they were kind of counting just up, whatever it happens, I'm going to tell you +1. And then there are these 2 errors here that are quite interesting. We call them, this is n+2, I believe it's kind of very intelligent error, if you want, because they knew that the answer couldn't be n+1, so they just said n+2. I mean, it must be something different, so let's say n+2. And this one, instead, I believe it's kind of a procedural error. They probably start counting from 1, and they got to n-2 before getting to the right answer that was actually n-1. Spatial order task, as you can see, we have something very similar here, with children are able more or less to do C+1, but C-1, the performance goes down. If we take a look at the errors, you have this massive error here, and this can be explained by this. I'll give you an example, okay? Here you have, here the child saw the number 8, here there was the number 9, and then the experimenter went like, this is 8, here you have 8, here you have 9, what number goes here? And of course the child said 10, because the child heard 8, 9, 10, so they answered C+2. What about mappers and non-mappers in these two tasks? As you can see, their performance is kind of similar. There are no huge differences. This is direction task, spatial order task, CP non-mapper, CP mappers. They showed more or less the same pattern of results. Let's see if we can correlate this with number word comparison to see what are the results, if what predicts, what correlates better with number word comparison. First, we start by entering like all these variables in this base model. That was our base model starting model, and we found out based on Bayesian analysis that forward enumeration and Krajcsi block were the best base model. And then we enter the status of mappers, the direction task, the visual order task one by one. As you can see, mapper is a good predictor in this case, so we are kind of replicating the results of previous studies. In the direction task, we only found that the n-1 predicted the performance in number words comparison. The same goes for c-1. And this is the best model in which basically this model includes all the variables, but the most parsimonious one is that one including the Krajcsi block and the direction task and the visual order task, but only for trials with n-1 and c-1. For the regression analysis for the digit the performance in the digit comparison task, again, we started with the base model in which we add the same variables plus the naming task, because of course, for performing a digit comparison task, it is important whether children are able to read the numbers by themselves or not. We found that the base model, I mean, the best base model was just the naming task. Here you have more or less the same results. As you can see, mappers, when is entered the singular, I mean, individually, it's good predictor. Same goes for direction task, but still only trials with n-1, and the visual order task, but only trials with c-1. When we look for the best model, we can see that we have naming, and again, the performance in the direction task, but only for trials n-1, and the visual order task, but only for trials that were c-1. So to conclude, we have this distinction between the successor and, if you want, predecessor function or knowledge. Most of children can do n-1, but fewer can do n. Children can do n+1, but fewer can do n-1. When they commit an error, they count up as they are applying a blind procedure. Of course, there is still one possibility that there is a role of inhibition. For instance, children actually know the answer, but they can help themselves. Like, oh yeah, it's +1, it's +1. They have this tendency to count. But I have to say that it is a possibility that should be explored. But if you think about the task, when there were small numerosities inside the box, for instance, they were perfectly able to perform the task. Even though there were 2 balls, one was removed, nobody said 3. All of them said 1, so it seems that they were able to inhibit the response. But it's something that, of course, it requires a little bit more of investigation there. Later graded principle, yes, we replicate the previous studies. There are some CP knowers that are mappers, some of them are not mappers. So we kind of found weak evidence that does relate to number comparison. I would conclude by saying that the knowledge of the preceding numbers we found that it relates to magnitude understanding, but as Attila was saying, probably it's like with asking -1, we are actually measuring the same concept, in the sense there are children that are giving you +1, but they really don't understand how it works. Instead, as soon as you ask for -1, you can reveal whether they have actually good understanding of the number sequence. I've presented you like one study that I've done with Daniela Lucangeli, but as there are many studies that are related to this one with my former and present collaborators, Ilaria Bertelletti, Roy Cohen-Kadosh, and Marco Zozzi. Great thanks go to all teachers and families and children and all the undergraduates that helped me in realizing these projects. And thanks to you for listening.
Thank you so much. That was fantastic. Darko, I'm really glad that you were able to get on. I made you a co-host, so if you just want to jump on and screen share.
Yep. One moment. There we go. Can everyone see the slides?
Yep, looks great.
Awesome. So let me first begin by saying my deepest apologies for being a little bit late for this. It was one of those mornings where like everything that could go wrong with my internet connection apparently did. But thank you to all of you who can stick around, and thank you to Francesco and others for organizing this. So in today's talk, I am going to tell you a little bit about how our intuitive number sense might help detect errors in symbolic mathematics. So to begin, I want to talk a little bit about two different ways in which our minds can represent number. One being the kind of intuitive number sense that we also sometimes call the approximate number system, or the ANS, and the other one being our formal sense of math that's very much supported by the kind of exact number concepts that the other people in the symposium have already been talking about. And at first glance, these two systems seem quite different from each other. So the approximate number system is approximate and automatic. If you take a look at these displays of blue and yellow dots, you'll effortlessly be able to tell whether there are more blues or yellows. But the sense is also approximate in the sense that as the numbers get closer and closer to each other, as the ratio gets lower, it will become harder and harder to make that discrimination. On the other hand, formal math is exact, it's effortful, it's based on learned procedures that we go through in order to solve it. And like another important difference is that the approximate number system has been shown to be innate and universal. It's found in non-human animals, it's found in every culture that we've looked at, in many non-human, in infants and newborns as well. Whereas formal math, and it's through its reliance on exact numbers, is slowly learned over a protracted period of time. It takes, years of grueling education to acquire. And so we can, in many ways, say that, the approximate number system appears to be this real marvel of natural selection and evolution, whereas formal math seems to be a marvel of human minds and ingenuity. And yet, despite these pretty major differences between them, work has repeatedly shown that that individual differences in our intuitive number sense actually predict formal math. And so here I'm just showing you results from one meta-analysis from Chen and Lee in 2014 that shows that across 36 different studies, both longitudinally and retrospectively in both adults and children, we find a small but stable effect whereby individual differences in the approximate number system predict formal math skills. And so the big question then is how and why? What is the actual mechanism that might support this correlation? And today I'm going to talk about just one mechanism that has frequently been proposed by many researchers but has not been formally tested yet. And that's the idea that the approximate number system might act as a source of error detection, that it might help us figure out when an answer that we solved formally using our exact number sense was perhaps answered incorrectly. And as a very concrete example, consider a child who is solving a math problem like 11 plus 19, and they follow a standard routine that they were taught, but they forget to carry the 1 and end up with an answer like 20. Now, one of the big challenges in doing mathematics is that when you solve an answer incorrectly, nothing in the problem itself tells you that you got the answer wrong. It's not like when you're learning to read, misreading a word might lead to a meaningless sentence. It's not like when you're learning social interactions, a person's expression might tell you that you said something wrong. And yet, nevertheless, many of us have the experience that when we solve an exact number problem incorrectly, that we at least have some sort of a sense that it's not quite right. So here's one proposal for how this might happen with the ANS. So simultaneously to solving a problem using our exact number sense, we could perhaps map these same exact numbers into our approximate number sense. And because we know that the ANS is likewise capable of doing basic operations like addition, subtraction, maybe even division, what this could result in is a kind of probability distribution, whereby we may be able to map a range of possible answers that would be considered acceptable in our approximate number system, and then compare the answer that we got symbolically to this, maybe realizing that, hey, the probability of this answer is a little bit on the low side. Whereas for children who have a very poor approximate number system, this probability distribution would be a lot flatter, a lot more answers would all register as equally probable, and they would be less likely to be able to catch this mistake. So we went out to empirically figure out whether there's any evidence for this kind of mechanism by first wanting to know, well, what this mechanism would predict is that individuals who have a particularly good number sense should also be better able to detect small mistakes in symbolic math equations. So that's what we did in both adults and kids. I'm going to first show you the result from the adults, which was recently published. The citation's at the bottom. And then I'm going to show you some preliminary work we've been doing in children. So here was the idea. We tested adults on 5 different tasks. So I'm primarily going to focus on the 2 main ones because the others were controls. We tested participants on an approximate number task, the blue and yellow dots, Panamath, for those of you familiar with that term. I'll show you an example in just a little bit. Here we're assessing how good an individual's approximate number system is. And we also developed this task called the equation monitoring task, where we gave participants math problems, and they had to figure out whether the provided answer was too high or too low. And I'll give you an example of that in just a moment as well. We also threw at them a bunch of control tasks to measure for various tertiary variables. We gave them an area discrimination task to measure general perceptual quantity abilities, as well as both a forwards and a backwards digit span to measure both working memory and operational memory spans. Let me give you an example of these 2 critical tasks. First, I'll show you the ANS task. Many of you might have seen this before, but for those of you who haven't, participants sort of see a display like this, and they have to very rapidly, without counting, decide whether there are more blue dots on the left side or the right side. We manipulate the ratio between the 2 numbers to make the trials easier or harder, and the critical dependent variable is accuracy. And the area task looks pretty much identical, except there's 2 blobs of different shapes, and they have to decide which one is larger in size. Now, in the equation task, on the other hand, participants were told that they were going to be shown a pre-solved equation on the screen that was always solved incorrectly. And they simply had to decide whether the provided answer was too high or too low. But critically, the display only stayed on the screen for 500 milliseconds, so they had to do this really quickly and intuitively. So you can give it a go yourself. I'm going to show you an example, and you can just decide too high or too low. And that was a relatively easy one. You probably could pretty easily tell that was way too low. Here's another example right here. Now in this case, the answer is just ever so slightly too high. And again, that's a much more difficult thing to do. And we're interested in, do participants who can tell apart even those really small differences really rapidly, are they also the ones who have a better approximate number system? So first, I'm just going to show you the results from sort of the raw the discrimination performance. On the left, I'm showing you the approximate number system results. And what you can see here is that standard ratio effect. And on the right side, what I'm showing you is the results from the equation monitoring task. I should note we tested both addition and subtraction. I'm showing you those results separately here. We also eliminated any trials that involved where any of the digits involved a 0 or a 5, just to prevent people from being able to use just a single digit to solve it. And you can see that in the equation monitoring task, participants could broadly do this. The average accuracy was in the high 60s. They were marginally better at the addition problems than the subtraction problems, though this did not interact with any other factor, and I won't really return to it much. And you also see that there's a decent amount of variability here, and that the distance between the correct answer and the answer that we provided predicted accuracy as well. But are these 2 in any way related to each other? So here I'm showing you the pairwise correlation, just a simple correlation between these 2 abilities. And you can see a pretty dramatic correlation between these 2, ANS on the x-axis and equation accuracy on the y. So in principle, then we can see that at least approximate number system individual differences in the ANS do seem to predict something about how well I can distinguish the direction and magnitude of the errors in the equation task. And by the way, this held when you separate just the addition trials and just the subtraction trials. It just wasn't driven by one of them. But of course, this correlation could have come up for any number of tertiary factors, or, people being more concentrated in the 2 tasks, working memory, IQ, who knows what else. So to really figure out whether the ANS, predicts equations even when these factors are controlled for, we did a regression where we inputted all of our additional control variables as well. And I'm showing you the standardized betas, and you can tell that the ANS continues to be a significant factor. In fact, it is the only significant predictor of the equation accuracy. And here is just that plot of that relationship when we take out the variability from the other three. So this shows us that what we find is that participants and approximate number system precision can, consistent with that account of ANS being used as a source of error monitoring, predict how well participants can tell the magnitude and direction of symbolic math errors. This is just one step in a long line of projects that we're working on. I can tell you a little bit about some ongoing work that we have that unfortunately is on pause due to COVID. But right now, one of the projects that we started but had to pause uses pupillometry, which has been in previous work consistently shown to be an index of prediction error of generation and catching of error magnitude. So we're using it as an additional index to figure out if participants are actually, if pupillary dilation is also a mechanism through which we can catch that correlation between those two. We want to know whether the relationship between the ANS and errors on these equation tasks actually mediate the correlation between the ANS and formal math. And we, of course, are also doing an experiment where we're trying to figure out whether the ANS predicts the errors that you yourself make in speeded addition and subtraction tasks. So all of these are ongoing. Well, they will be ongoing once we're allowed to test again in person, so stay tuned for that. And in the last little bit, I just want to tell you a little bit about the developmental story as well. So whether this is also true in children or whether this is some sort of a relationship that really only emerges quite late. And to do this, we needed to reappropriate that equation task because we couldn't give children little equations and ask them whether it's too high or too low. We took inspiration from work by Rochelle Gelman and others and introduced the task in which children were presented to a puppet who would then solve age-appropriate math problems. So, for young kids, they would be simple problems like counting, and for older kids, they would be much more complicated problems like complex word problems with, even some division and complex subtraction. So what the child would do is they would be introduced to a puppet, and the experimenter would ask the puppet to solve a math problem, and the puppet would either do so correctly. So for example, they would just count backwards from 10 and they would do so correctly, or the puppet would on half the trials do it incorrectly. They would make either a small error, like they would just miss one number, in this case, the 7, or they would make a major error and skip maybe 5 numbers or so. And likewise, when they would be solving addition problems, they would sometimes make a small error, they'd only be off by 1, and sometimes a big error, they would be off by 5 or more. So here we tested kids between 5 and 8. Again, the errors that they experienced from the puppet were drawn from age norm data from the team of 3, such that we could give older children more advanced problems that were appropriate for what they could do. In this particular experiment, we only tested the approximate number system and this math error detection. There were no additional control variables. That's the next step that we're working on before COVID. But for now, all I'm going to show you is that whether there is any relationship in children between these two abilities. And here what I'm showing you is a regression that demonstrates that indeed there is, how well children can detect the mistakes that the puppet makes, deciding whether the puppet solved it correctly or incorrectly, is predicted quite robustly by individual differences in their approximate number system. Age also makes an impact on here, even though we tried to make older kids solve harder and harder problems, but other variables like gender do not. So to very quickly sum up, what I showed you today is that individual differences in the approximate number system predict the direction, the detection of the direction and magnitude of errors for basic symbolic math operations. This holds for both adults and children. In the case of adults, we were able to control for a number of other tertiary factors. In the case of children, that work is still ongoing. And so this is, of course, just the very beginning of a much longer road of trying to really demonstrate that this could be the mechanism. That's going to involve a combination of mediation analyses, pupillometry measures, et cetera. But it meets that very first test of demonstrating that, in principle at least, the approximate number system seems to be involved on these kinds of error detection tasks in symbolic math. So I want to thank you all for listening today, and I'd be very happy to get any questions.
Thanks. Good. Well, now I would say that if there are questions, you can type the question if you wish. You can speak directly as you prefer. I'll wait some seconds to see whether someone has got a question.
Attila, did you want to ask your question?
Yeah. Thanks for the great talk, Darko. I have I guess a usual question. So whenever you are measuring number sense, then even if you're controlling for perceptual properties, still you can measure with the same task the number sensitivity, perceptual sensitivity, and inhibition, and maybe some other things, and in a unknown combination. So do you have any consideration what you are measuring and why? So could you exclude those other non-numerical factors?
Yeah, I think that's a great question, and I think a common and important one for everybody who studies the ANS to deal with. Let me give you the short answer and then the slightly longer one. The short answer is that we always, including in this particular sets of experiments, examine congruency effects. So whether both children and adults perform differently on the trials where in this case, primarily cumulative area and convex hull are congruent with the answer versus incongruent. And some people over the years have suggested that this congruency effect might itself be a measure of inhibitory control, that children and adults who have better inhibitory control will be less susceptible to using the non-numeric cues, and children who have worse will be more likely to. What I can tell you is that in neither experiment, neither with the adults nor with the kids, and these are not the only two experiments, we had a bunch of pilot work that got us to this point. So in none of the experiments have we found that congruency effects predict any of the error magnitude, so to speak, variables. In the case of adults, we simply don't find any congruency effects at all. In the case of kids, we do find some congruency effects, but they do not predict anything. Yeah. Now, that's the short answer. The long answer is, are congruency effects the best way to measure inhibitory control? There's a lot of debate about that as well. Work from Liz Brannon's lab, I know, and others has really wondered whether that is the best way to measure it. In the sort of new work that we're doing with kids, or rather, I gotta keep saying this, that we were doing before COVID, we do have a battery of executive control and inhibitory control tasks as well, in order to make sure that we really have that as tightly measured as possible. We're using the day-night task and the flanker task essentially for the kids. So that's the sort of stay tuned for that part.
Thanks. Any other question from let's say the audience? See whether someone types something. Okay, I have a question though. Attila, could you, you talk a lot about the given number task, but of course you're working on this and you're developing probably new version that's going to be more reliable and so on. But you mentioned this before, but what are your suggestions if someone has to use the given number now, but not now probably because of the COVID, but generally speaking, what are your recommendations to use the task in the most effective way?
Well, I have only some kind of trivial suggestions. So for example, when we can see that there are large number subset numbers, it means you shouldn't stop measuring numbers at 4 or 5, but you should keep going on. And about the noise, you shouldn't use the titration method, but you should measure the whole range and this kind of gradual measurement, and maybe introduce some sigmoid or some other method to have a more reliable parameter or something like that. So my best guess would be that based on every single issue, you might have a fix for that would kind of modify the original task, and that modified version could be used in future studies, and then we could see whether this will solve the other problems. For example, the validity problems you are working on. So, CP nowhere category will not really predict, for example, this subtraction problem and so on. So that's my only guess. And I don't have any specific alternative task to use instead of the given number task.
Thanks. Any question from the audience? Otherwise, I have one for Emily. Emily, okay, you showed that, I mean, like, of course, children have to understand this distinction between something that is continuous and discrete. Do you have any data, or do you know, like, because I'm not actually sure about this, but any evidence showing, you know, like, of course, if children are shown like 10 dots and they are like asked to estimate it, they can provide you a number. What happens if you show something that is small? Let's say you can frame it as a sort of game, if you, or something like, you know, like, this is a box. You know that the small box, just one person to move it, but this is like a big box. How many person do I need? How many people do I need to move it? You see, in that case, it would be continuous, but probably still showing a relation between the magnitude that is continuous and the counting list. Do you have any evidence of this, or?
No, I mean, I don't personally. I appreciate the question. I have to think about it for a minute. I think it is all worthy of exploration in the sense that we do see that this is something that children are disentangling as they move through these the developmental trajectory, however it is characterized based on the insight provided by our colleagues here. I'd have to, I think that there are a lot of questions to be asked about how children are extending number words. And we know anecdotally that they're quite likely to characterize things that are bigger as having more, right? More numerically, not just in the continuous domain. So I'm sorry, I don't have an exact answer to that question, but I think it's one that's we should consider. I think we need to continue as per, you know, very early work looking at the difference, the distinction that even the youngest infants can make between continuous and discrete quantities. Continue to look at that, but not just controlling for it, but actually looking at exactly how children are thinking about both dimensions or numerous dimensions as they move through this.
Thanks, great. If someone has got a question, you can type it, or you can stop me because I have another one for Emily. You show that there is a difference for 3 knowers. I mean, in perceiving difference, continuous, discrete, etc. Why 3 knowers? Is there a relation with singular, plural, 1, 2? What do you think?
Yeah, I definitely am interested in that. And I do see that there is an influence of linguistic context on children's understanding of number words and how they're extended to discrete and continuous quantities. The work that we have been doing, and my colleague was on the call earlier, but mentioned that it was midnight where she was, so she had to head out. But she and I and others are publishing work that looks at a cross-linguistic comparison, noting that different languages make that distinction between singular and plurals differently. And we were making the comparison with Mandarin Chinese and the classifiers that they use, and whether that's an indication that from very early on, number words are going to always be paired with discrete countable objects because they are always paired with those classifiers. Whereas in English, it would be the association with the singular plural marker, as you mentioned. So there's a linguistic element to it, but there is also the understanding that you could be extracting what you know from what you know, right? So you know what 1 is, you know what 2 is. Now you have 2 data points by which to make inferences about the rest of the numbers in your count list. So I'm really interested in exploring that further and better understanding the role of language and linguistic context, and then also just this kind of the induction that children might be making based on what they know. More of a conceptual account.
Thanks. Any question from the audience?
I see a preprint coming out. I'm going to look for that. Thank you for sharing.
Great.
Very interested in that.
Thanks, Mo. Good, perfect. I'll wait 10 seconds because I have another question in case. But this time is for Darko. Darko, you talk about this error detection mechanism. How do you square this like ANS with this thing like that when people are asked to estimate the numerosities, they actually underestimate a lot. So can you comment on this?
Totally. A great question, and one of the big things that we care about a lot in the lab. One of the things that I think is important, so the question of why people underestimate is, I think, a very important one. There's a lot of different views on that. My view, and we have some data consistent, I think, with this as well, is that the effect actually is maybe primarily driven, let me put it this way. I think there's a distinction between estimating a visual quantity and mapping an Arabic digit to the approximate number system. In other words, I think that you're very frequently going to find underestimation effects when, for example, I show you a bunch of dots, or maybe I play a bunch of beeps in your ear, and I ask you to estimate the quantity. And there's many different reasons why that might be. Stipe Anadosi has a recent paper in PNAS suggesting that perhaps that is from a kind of accumulation procedure that you're doing. I actually suspect that it's more likely to have with things like dots being in the periphery and crowding, and sort of like issues with that the COGS could also clear up a little bit, but not entirely. And so I think that the underestimation effect is primarily going to be observed in due to the actual encoding, the perceptual encoding of the of the stimuli, whether they be dots or beeps. But in the case of error detection, I am just dealing with Arabic digits, and I can map those transparently to the correct position on the approximate number system, such that I don't think that you're going to experience any kind of like significant underestimation effect from that. Where I do think that you might find an interesting deviation, for example, is if, for example, what we were doing is if we were asking you to somehow, do the addition of dots, like if I presented a bunch of dots and I asked you to add them, and then simultaneously, presented you with some sort of a symbolic thing, I think there's a chance that those could dissociate, because again, in the encoding of the dots, I think is where the underestimation effect is really stemming from, rather than in the actual relationship between the symbolic numbers and the ANS itself. But that's an open question about what is the source of the underestimation effect, but I just think that it's more likely to be sort of in the input side to the ANS rather than in the relationship between symbolic numbers and the ANS itself.
Good, thanks. Thanks a lot. Any question? If you're shy, you can type it. No question coming from
That's good, and we're substantially over time now. So
yeah.
Thanks to everyone who was able to hang out longer today. It ended up being a really great symposium. Not that I'm surprised.
Thanks for organizing this. That was great. I mean, like everything worked perfectly.